Hi everyone, we are Group 5 from Session 8. This is our digital logic project, which title is Electronic Leaf Controller System by using deep flip-flop. Next. This is the content that included in our presentation slide. First of all is introduction. Second, system requirement. Third, system implementation. Fourth, the circle. And the last is conclusion. Next. For the introduction of background is which the rapid growth of modern building, leaf controller play an important role in ensuring safe and efficient movement between floors. In this project, we designed and simulated a leaf controller for an 8-level building. As Group 5, our objective was to implement the system using deep flip-flops to create a 3-bit synchronous up or down counter. This project allowed us to apply the theoretical concept we learned in the digital logic course to a practical real-world system. Next is the problem statement. The main problem in designing a leaf controller is ensuring proper coordination between user input and the current state of the leaf. Without an effective control mechanism, issues such as incorrect flow movement or unsafe operation can occur. In this system, the controller must accurately track the current flow using a 3-bit deep flip-flop counter and compare it with the flow selected by the user. Based on this comparison, the system decides whether the leaf should move up, move down, or stop. Additionally, the leaf is designed to operate only when all safety conditions are met, including master power activation, start control, and correct 4-digit password authentication to enable the system clock. Next. For the suggested solution, to solve the identified problem, we propose a digital leaf controller implemented using a 3-bit synchronous up and down counter built with D flip-flops. The solution is divided into two main parts. In the first part, the basic leaf controller focuses on flow tracking, direction control, and automatic stopping. The 3-bit counter keeps track on the current flow, where a comparator compares it with the user selected flow. Once both values match, the system disables the clock to stop the leaf smoothly at the destination. For the second part, an advanced controller is introduced to enhance system security. A 4-bit password authentication mechanism is integrated, where the leaf system can only be activated after the correct password is entered. This authentication controls the power and clock-enabled system signal, preventing unauthorized operation. Overall, this solution demonstrates a secure and reliable leaf control system using practical digital logic concept. Next. This is our block diagram. This diagram shows the overall block diagram of our leaf controller system. The user select the desired flow using the 3-bit switch, which are displayed on a 7-segment display. The current flow is tracked by a 3-bit up or down counter and also shown on another 7-segment display. Both values are sent to a 3-bit comparator, which determines whether the leaf should move up, move down, or stop. Once the current flow matches the selected flow, the comparator sends a signal to the clock disabler to stop the counter, and an LED indicates arrival. For security, the system only operates when the power and start buttons are active and a correct 4-bit password is entered. The password is verified using a 4-bit decoder, and a confirmation LED light out when authentication is successful. Thank you, and I will pass to my group member. Thank you.
Okay, next, we have our leaf controller part 1 basic system. So our project is a digital leaf controller system designed for an 8-floor building. So each floor is represented using 3-bit binary encoding from floor 0 to floor 7. The leaf supports bidirectional movement, meaning that it can move upward or move down, depend on the selected directions. So for safety and correctness, the leaf only moves when three main conditions are satisfied. First, the door is closed, and then second, the desired flow is selected, and the current flow is not equal to the desired flow. So the current flow is tracked using a 3-bit synchronous up or down counter implemented with D flip-flops. A 4-bit comparator continuously compare the current flow value from the counter with the desired flow input from the user. When both values match, the comparator disables the clock signal, causing the counter to stop. This ensures the lift automatically stop at the correct flow. The current flow status is displayed using LEDs or a 3-segment display. Next. So next is part 2, our advanced controller security system. So in the advanced controller, a security authentication system is added to prevent unauthorized use of the lift. The lift can only be operated by authorized users. So before the system can start, the users must enter a valid 4-digit password. The password is represented as a 16-bit binary input where each digit uses 4 bits. Password verification is implemented for 4 bits. For four 4-bit decoders, each decoder checks 1 digit of the password by decoding the binary input and comparing it with a preset security code. So the output decoder are connected to an AND gate. The output signal called password valid becomes high only when all 4 digits are correct. This password valid signal is connected directly to the clock-enabled logic, ensuring that the lift cannot start or move unless authentication is successfully. Once the password is verified, a tick icon LED and a 7-segment display provide visual confirmation that the system has been unlocked. Next. So here is our system implementation. We have a state diagram and also have K-maps from the transition table. So next. This is basically our transition table that have present state, input, next state, FF input and operations. So next. So this slide shows the overall system overview using a block diagram. It explains how all subsystems are connected and work together. So on the left side, we have the input switch that allow user interaction with the system. This include 3-bit flow selection, 16-bit password input, and the power and start switch. So next in the middle, we have 4-bit decoders from the core of the password verification system. They decode to binary inputs and enable the system only when the correct 4-digit password is entered. On the right, we have clock disabler that is implemented using a fine input and gates. So this block control whether the clock signal is allowed to reach the counter. So the clock is enabled only when all safety and security conditions are satisfied, including the door close, valley, flow selection, flow mismatch, direction control, and password verification. So next, I will pass to my group member.
The next component of our system is the D flip-flop, and it acts as the system's counter. It's used to track the floors, and also it operates via a clock generator to start or stop the counting based on the clock disabler. The next is the 3-bit comparator, and it used to monitors between the target floor levels and also the current floor levels. It used the XOR, NOT, and also NAND gates to detect a match and stop the lift upon arrival. The last component is the 7-segment display. It provides the constant visual feedback, showing both the current floor and also the hexadecimal values for the password reader. Next is the system operation. In this part, we have four stage, which is the first stage is the authentication. The operation will begin with the security, and the lift is only will energize when the power and start switch are in high, and also the 16-bit binary password is validated. And the second stage is the selection. Users will interact via the input surface to choose a target floor from 0 to 7. The 7 segment display provides the immediate visual confirmation of the selection. The next stage is movement. The clock disabler acts as the system brand. It will allow the 3-bit synchronous counter to move the lift only when all the security and safety conditions are met. And the last stage is arrival. The comparator will monitor the arrival, and once the destination is reached, it will cut the clock pulse, and we will also use the saturated logic to ensure that the lift stays safely within its boundaries. Next. Next is the advanced system controller. So in this part, we have enhanced the design by adding a 4-digit password authentication module as our primary access control mechanism. So the password authentication use the 4-bit decoders to translate the 16-bit binary inputs into a 4-digit security code. This is mandatory for all operations. And the next is the master system enable. So we will use the 4-bit decoders to process the user's binary input. Unlike the standard systems, this is a mandatory step for every operation. So without the correct code, the lift will remain locked. If the password is incorrect, the clock signal is blocked, so the lift cannot operate. The password output is tied to our master system enable, which is 5 input and gate. This will create a hard interlock where the lift only response is if the power, start, and also password conditions are all satisfied. So by making this authentication as a pre-operation condition for the clock disabler, we successfully prevent any unauthorized movement of the lift. Next. I will pass to my group member to explain the disk circuit.
So this is our disk circuit, and later we will show in our demonstration video. This is the following circuit. And for the conclusion, this project demonstrates the design of a digital lift controller for an 8-floor building using D flip-flop and logic gates. The system accurately tracks the lift's position, only moves when doors are closed, and stops automatically at the selected floor, ensuring safe operation. We implement a saturated counter to prevent errors and added a 4-bit password for security. While the lift currently handles one request at a time, the project gave us hand-on experience in turning logic tables into functional circuit. Future improvements could include handling multiple floor requests and adding an emergency stop for enhanced safety. So now we will present our demonstration video. So we start with our app simulation first. First and foremost, we should key in our password, which is 9C0A. Then we can open the start and power button and select our desired floor level. Then we can click the up-down button and push the push button to let the lift go up. After our current floor level is same with our desired floor level, the arrival indication will show white. And that's all for our up simulation. Same with up simulation, we can just choose our desired floor level, then we can just change the up down level button, then we can just push the push button to go down the lift. After it arrives, it will show the arrival indication become white. That's all for our simulation.